meaning to us, and he is now the big celebrity on campus. Here you see in March 20th was his first return to Ohio State since he won the Nobel Prize. And we gave him a red carpet welcome. And I want to point out in the background, is there a pointer?
Pointer.
You notice that character in the back? That's Brutus the Buckeye. That's Brutus the Buckeye. He only shows up at football games, but he came to welcome Agostini back to Ohio State. So,
Big celebrity.
big celebrity, that's right.
Football, right?
And so today the talk will be about recollision, but a different type of recollision driven by attosecond pulses, not tunneling. Okay, this is
In this computer, this will work. It's like that.
I'm not sure what. Yeah, oh, that's working. I'm sorry. Well, it doesn't matter. It was just.
Was it a cartoon or something?
It was a photograph of Feynman, so
Oh,
we can do without it.
He's Feynman.
But, you know, what was Feynman's lesson to us, or one of his lessons to us? Feynman taught us that a quantum process is dictated by the sum of all quantum trajectories that contribute to it. This is the essence of the Feynman integral approach to calculating. And what he said is that we analyze based on trajectories, and yesterday you heard a lot about trajectories in terms of this three-step model. We analyze based on trajectories, but we don't necessarily measure them, right? We measure this coherent sum of trajectories, and that's what the measurement is. So what I want to talk about today is how can we use attosecond pulses to kind of deconvolute these trajectories, select trajectories, and see what the physical outcome is for just subclasses of trajectories. And each of those subclasses of trajectories, if you can coherently sum them, should equal the total quantum process. So let me say a little bit about the history of the formation of attosecond pulses. Well, strong field physics, this three-step model, gave us the intuitive insight into how one could form attosecond pulses, okay? And as it was explained yesterday, it's a process where the electron is tunnel ionized. It's then picked up by the field, propagates, and then comes back and interacts with its own core. So there's a cartoon of the three-step model. And the three-step model was responsible, as I said, to give us the insight to form attosecond pulses. So today's talk is how can we now use attosecond pulses to learn more about strong field processes. So the alternate title for this talk is the payback. And I put this into the talk especially for Bob. Okay. Okay, so here is the three-step model. The three-step model. Ionization occurs by tunneling. This is something that had been studied since before the laser, of tunnel ionization in an optical field. What you do then is you free a wave packet, and that wave packet is now driven by the strong electromagnetic field. So the electron comes off, propagates, and for certain trajectories, you can think of these as classical trajectories, it can come back and recombine and emit a higher energy photon. Okay, so that's illustrated here, and as I said, this model gave us a simple, intuitive view of strong field interactions in the tunneling machine. And let me be clear, this is a classical picture, or quasi-classical picture. The quasi part is tunneling, which is purely quantum mechanical, but the rest is all Newton's equations.
Right.
Okay. Now, the thing to notice that once the wave packet is tunnels on the outer turning point of, say, the Stark potential, then the electromagnetic field that you're imposing is stronger than the Coulomb, and it dominates the motion of that. So now you can apply Newton's equations, okay? And thus, this Pond-motive potential, that is the quiver motion of a free electron, becomes a key ruler for you to make predictions based on these classical quantities. But everything depends upon the fact that you're tunnel ionizing. The initial conditions for which trajectories get launched depend upon the tunnel ionization. And that's strange. The video plays, but yet the picture of Feynman won't show up.
Maybe it will now if you go back.
Okay, so here's my cartoon of the three-step model. The electron is picked up, tunnel ionizing, picked up by the field, propagates, and then recombines, okay? So the energy, and we talked about this yesterday, the cutoff energy is defined by this lambda squared because it's the propagation that puts the energy into the electron. So you can calculate the cycled average energy of a free electron, and it's a good assumption then that this is a free electron or quasi-free electron. So that's where the lambda squared scaling comes from. So it's actually rather simple. The reason you have a higher energy cutoff in harmonics when you go to longer wavelength is because the electron is spending more time, because of the period is longer, picking up energy from the field. Okay, so you can do all this. So classical trajectories have different release times, that is phases of the field at which they tunnel ionize. They have different propagation times based upon those release times. And therefore the harmonic emission times and energy also depend upon those initial conditions. And you can sit down with Newton's equations and calculate various quantities. One quantity that when I was working with Kuhlander, when we kind of saw this model, is that you can calculate and say, what's the maximum energy a free electron can have if it's released in the field? And that number is 3.17 times this Pond-motive energy. So this is where the cutoff rule comes from. Where 3UP, just you can see it classically, why it's there. Now, I'm showing here the emission of harmonic photon in the cartoon, but the electron doesn't have to recombine to its ground state. It can just elastically scatter off the core, and that gives the electron even more energy than it would have if it didn't interact. And that brings the energy at 10 times this Pond-motive quantity. Okay? So typically, our Pond-motive energies, if we're working in, say, the mid-infrared, could be 100 volts or more. So we can produce electrons out to like a kilovolt from a single atom. Let me be clear about this. This is all single atom physics that I'm talking to you about. And because of the fact tunneling has this exponential rate that's peaked at the extreme of the electric field, the process of depicted in the three-step model is inherently sub-cycle. So the reason that you get attosecond pulses is not through any magic. It's just the fact that the physics that underlies it is attoseconds in nature. Okay. So when this model came along then, there were a number of phenomena that were being observed in the late 80s. Things like above threshold ionization, which Agostini first observed in like 1979, high harmonic generation, what Anne Louier studied, discovered in like 1988, and then multiple ionization, which was studied since the beginning of the laser. People were interested in the concept of just putting a large amount of energy into an atom, right? And there's obvious reasons people are interested in putting a lot of energy into an atom, okay? And what happened was this model unified all these phenomena which were treated independently up to that point by different theories and so on. And this said, all of this comes from this one process. Okay, since tunneling is the key to this, let me spend a little time having you think about tunneling for a moment in an optical field. What you have is, at any moment in time, you can think you have a strong enough field that the barrier, the Coulomb, gets suppressed such that the electron has some rate of just tunneling through the barrier. You could imagine if I have a strong enough field, I can just classically ionize the electron. It just goes over the barrier. Okay, think about this spatially. What you have is this Coulomb potential now that gets distorted, and the electric field is along one direction of space. So the tunneling barrier is kind of like a little aperture in space. And so all the tunneling wave packets look very similar, okay, because it basically gets spatially filtered. So it doesn't matter so much on the details of the atom itself, except its binding energy. The wave packet that is born finds itself at the outer turning point of this barrier with near zero energy and kind of a Gaussian shape. Okay, I just say that with near zero energy. And the wave packet then, because of the fact that tunneling is exponential in the electric field, the tunneling has its initial phases fixed by the rate. And since the rate is exponential, you can see that the tunneling rate is then peaked at the maximum of the electric field and drops off rather rapidly. So this is defining my initial phases when I do a strong field experiment. I can influence it a bit, and people have, but I don't have robust control of the initial conditions. Okay, and because of also because it's highly nonlinear, that means if I want to study this process, since the rate grows exponentially, I have a very small intensity window in which I can vary my parameter to study this process. So there's a lot of constraints put onto your observations based on this exponential behavior. Okay, so this is for Bob. So as I said, this is the payback. Strong field led to the discovery of attoseconds, okay? And as soon as people saw harmonic comb, when Anne first discovered the harmonic comb, people immediately said, well, you can form very short pulses. You have all this bandwidth, right? It wasn't until later that it became clear how that bandwidth, how the phases of that bandwidth would behave. And the three-step model plays a role in trying to understand how those phases are behaving. But the strong field community, had discovered this high harmonic generation. So this guy is the strong field community. But the ultrafast community heard that possibly you can get attosecond pulses. So they come along and they go to the strong field community. They want this attoseconds, right, to do their pump probe type of experiments. And they said, You know, what do you want of me? I'll give you anything you want, but do what I ask, okay? And the strong field community talks back to the ultrafast community and says, well, someday, and that day may never come, and you know that's not true, right? I would like to call upon you to do me a service in return.
My grandfather used to say that.
So I'm going to spend the rest of the time talking about that repayment to the strong field community. Okay, so let's start with the basic idea of what we're going to do. So we call this method quantum trajectory selector, okay? And what it is attosecond control of ionization in a strong field, okay? So here's the cartoon again, here's the electric field, here's the tunneling rate, which is fixed at the peak of the field. ADK is just stands for Asimov, Delony, and Pranoff, who basically developed this model of tunneling in the DC limit. What we're going to do is get rid of tunneling. Okay, I'll tell you in a moment how we get rid of it or minimize it. And then we come in with an attosecond pulse. And we shape the attosecond pulse such that it frees an electron in an atom close to threshold. That is, it produces a near zero energy electron. And we do that in the presence of a strong optical field, which now picks up the electron just like it did in the three-step model and propagates that electron. And then hopefully that electron comes back and interacts with its own core. So it's a coherent process that we're trying to drive here. So you can think about this as photoionization, or single photon ionization induced Reed collision. And once we can do that, now, since we have an attosecond pulse, which is ionizing radiation, we can now vary the delay as long as the XUV is phase locked to my external field. Okay? So that's the principle. And then what you would hope to see, and here's just a photoelectron spectrum that we've taken. So you're looking at the electron energy versus delay. And you can see the electron energy is modulated, okay? And if you Fourier transform that, you find out it's modulated at 2 times the frequency of the optical field. And that makes sense because this attosecond pulse passes and ionizes in each half cycle, so it's twice the frequency. And the other point I should make here is that we don't use isolated attosecond pulses. We actually make trains of attosecond pulses, and those trains of attosecond pulses are separated by either twice the fundamental frequency or at the fundamental frequency. We can manipulate that, okay? So we use trains. So I think yesterday we heard Peter talk about just the Fourier transform of a train in time into something that's periodic in frequency. Okay, so there were early attempts at trying to do the experiment I'm going to describe to you today. A lot of the motivation initially was, can we use this idea of seeding to increase the yield of high harmonics, that is, increase the number of photons. So people went in the lab and tried to seed XUV into a gas jet in the presence of the strong optical field and see if the harmonics that they observed are enhanced by the seeding. Okay, so in many ways like an amplifier. So the early experiments, the theory was done by Ken Schaefer, experiments done by Ursula Keller's group at ETH. They saw about a 30% increase in high harmonic generation, which, you know, wasn't a big win for the ethic. Later on, Mark Vracking, at that time he was still, I believe, in FOM in Amsterdam. Mark went ahead and again he saw a minor increase in the harmonic yield, but he did see the modulation at 2 omega, as you might expect if the seeding was working. Okay. And then later on, a rather Herculean experiment was done by Nurit Dadovich. And what Nurit did is basically built an interferometer. She didn't learn much about the quantum trajectory selection from this experiment. You know, I talked to Nurit about this. It's an experiment that she will probably never go back and attempt to do again. It was so hard. And again, the returns were modest. Okay, so now let's talk about how we're going to get this method to work. I mean, why are we going to succeed when the other people early on, in a sense, did not have much success? So I think now you have the basic idea. What we're trying to study is XUV initiated recollision in a strong field. Okay.
So are you saying there are two pulses going in there? One that causes ionization?
And one that drives the electron once it's free, yes. So it's the three-step model, if you will, but the first step is photoionization, not tunneling. And step 2 and 3 are the same as you would,
I see.
okay. So again, this is not playing correctly, but here's the idea. Again, we're going to launch trajectories, so we're going to park our attosecond pulse in reference to the strong field at different delays, and then launch subsets of trajectories. And we can launch and study trajectories at any phase we choose, right? We can initiate ionization at the node of the electric field where the tunneling rate is 0 and still study the strong field physics at that phase. And as a consequence then, just like in the three-step model, we expect that the observables will be still high harmonic generation, elastic scattering, or inelastic scattering. That is, looking at the electrons or looking at the charge state distributions. So how do we go about and do that? So as I said, we want to shape an attosecond pulse, an XUV pulse, such that it's near threshold for the system under study. So we would like the harmonic Q omega, that order, minus the binding energy to be near 0 energy electron. But we want to drive recollision. We want to impart energy into the electron. And therefore, we want large pondomotive potential so we can make use of this pondomotive scaling, this pondomotive rule. But we want the rate of single photon ionization to dominate over the tunneling rate. And ideally, we would like the tunneling rate to be 0. Okay? So what's the solution? The solution is to make use of this lambda squared scaling of the strong field in order to meet the objective of large pondomotive potentials, large UP, but we can work at low enough intensities of the fundamental field such that we don't drive much tunnel ionization. So that's the key, that what we're doing differently. So here, let's quickly look at how we do the experiment. So typically, we're running in the 1.8 to 2.4 micron range of our laser. We get the laser, we have a beam splitter. The majority of the light goes in, focuses into a gas jet where we form harmonics. The remaining mid or near IR light goes through the second arm of our Mach sender. Okay, then we recombine them, and they both get focused in the center of an end station that contains an electron spectrometer and a mass spectrometer, so we can study the electron energy, or we can study the mass over charge distribution of what we're creating.
So you have two gas jets? Or
No, well, this is not, this is high density here to generate photons. This is just an effusive source. So we introduce, so we make the harmonics,
Where?
we make it right here.
Okay, that's
Okay,
that's
and then the harmonics propagate, hit this mirror, and focus. And here we introduce the atom we want to study, or the molecule.
Okay.
So that's the target.
The other beam is doing what?
And the other beam gets recombined, and that's the strong driving field.
That hits the sample where you have argon.
Yeah, yeah. So both of them are present, and because this is a Mach center, we can vary the delay very precisely. Okay.
So this is like a Kerr effect in a way, and in this sense.
Well, but it's a single atom.
I know, but I'm just saying, you get a pump and a probe. more or less.
It is a pump. Yes, you can think it's a pump and a probe that have to be coincidence in time.
Yeah, you can move it back and forth. It's like the
Yeah.
Kerr effect that first polarizes, and you get two beams, the pump beam, and then you have another beam.
Yes, I don't know if I recall the curve. Yeah,
Well, you'll have to look it up.
let me think about that.
It's okay, you can think about it.
Okay, thanks. Okay, we want as I said, we want the single photon ionization to dominate over tunneling. We never really can get rid of tunneling completely, so to meet that objective, we want as many photons as we can get out of the source. So we play tricks there, how to optimize that. As I said, we also want to shape the XUV such that it's creating almost near zero energy electrons. Okay, here's a spectrum of the harmonic cone. Okay, and here is the binding energy of argon, say. And you can see we have one harmonic tooth that is near threshold. That's creating our harmonic. And we can tune that around because we can tune the wavelength of the mid-infrared. Okay, so that's the basic idea. We shape it. We can control the frequency of the train by using other tricks that is known in the field. We know what the temporal profile of this Attosecond train looks like by using a method known as Rabbit, which is a way of characterizing the phase of the harmonic light. So we measure both the amplitude and phase. Once we know that, we know what it looks like temporally. And finally, different than the early experiments, we're not going to look at harmonic generation. Harmonic generation is complicated by the fact that Maxwell's equations matter in the harmonic process, okay? What we're interested in is what is the single atom response looking like? What Bob talked about yesterday, what is this distortion of the electron cloud looks like? That's what we're interested in. And so what we do is we look at charged particles, which is truly a single atom sort of measurement. Okay, so let's see if this works. So we're going to launch this wave packet with photoionization. That wave packet gets picked up by the field and then driven back to the core. And if it has enough energy, just classically, if it has enough energy that exceeds the binding energy of the second electron, it can knock it off through an inelastic process. Okay, this is well known in strong field physics, by the way. Okay, so that's the idea, is let's look at the formation of a double ion in the presence of this two-color field, XUV plus mid-IR. And so here you're looking at a mass spectrum. This is the M/Q for argon 2+, so the double ion of argon. And now we're varying the delay, like I told you, and you can see that the argon yield is oscillating. And it's oscillating at 2 omega, just like you would expect by a field-driven process, okay? So let me make this clear what's going on here. We can launch trajectories that create double ions at this phase. We can maximize the phase by our choice of delay. And if we move the attosecond pulse train here, we get a minimum in the double ion yield. To make the point even clearer is if you just let the mid-IR in alone, that would just give you a DC background. That is a very small contribution to what we're seeing here. It's less than 5% normally. It depends upon the intensity we're using in the experiment. And the XUV alone produces no double ionization, okay? It only if you look at the mass spec, you only see the argon single ion.
Where do you put the laser pulses on the top diagram? You got the first electron coming in out this side.
Yes.
Where do you put the lasers in? You get the first electron goes around, the same electron went out.
Yeah, so this is all happening in a half cycle. So just like the recollision model, you photoionize, and then the wave packet gets picked up by this strong mid-IR field, driven out and back. But when it comes back, it has more energy, right? It's been accelerated in that field. Okay? And I won't, just for the sake of time, we can actually do calculations and we see interesting effects here. For instance, you would think classically, in order to free the second electron, you need to have the first electron return with kinetic energy greater than the bind energy. In fact, that's not the case. You can even excite below threshold and get contributions to double ionization through, again, one coherent process. Now, one of the early signatures when people started to observe any strong field effect, but especially a signature of the three-step model, is that if you change the polarization to linear to circular, rescattering, recollision shuts off, right? Because in the linear field, the electron does this, but in the circular field, the electron drifts away and never returns to the core. So it's very sensitive to polarization, this strong field process. And this is just a demonstration how XUV-induced recollision is indeed polarization sensitive. Here's linear polarized light, here's circularly polarized light. And you can see we attenuate the amount of double ionization by almost a factor of 10. And the reason there's residual is because our initial conditions are not exactly tonal, okay? So there's always some probability of a return under our initial conditions. Okay, so let me tell you the really fun part. And here you're going to have to accept, this is known in strong field physics, okay? Now what we do is we collect the double ion in coincidence with the photoelectron spectrum. So here you see in the photoelectron are modulated at 2 omega. So they're also sensitive to the phase at which we launch these quantum trajectories. Okay, again, just to make the point clear, at this phase here, I maximize the energy of the photoelectrons. I basically streak them in the field, okay? At this phase here, I minimize the electron energy. Okay, what can I do with this spectrum? Well, I know that there's trajectories, and they kind of dominate the ionization that never return to the core. They either just wiggle away from the core, or they come back to the core, but they come at large impact parameters. And so most of the ionization is dominated what we call direct electrons. Those are electrons that don't interact with the core. And what do I know about that? What I know is that a free electron has its maximum momentum when the vector potential is maximum, okay? So I should see a maximum in the electron energy when the vector potential is a maximum, or to say it in other terms, when the electric field is 0. Okay? So we look at this spectrum. We know that these kind of orange-colored electrons are the direct electrons. And we can now say, okay, this is maximized at the maximum of, this is the vector potential, not the field. Okay? So now we set it equals 0 in our experiment. And now we can look at the other observables. We can look at elastic scattering, we can look at inelastic scattering, and time with attosecond precision when those trajectories or those wave packets are launched. And that's what you see here. These lines are representative of when both the double ionization and inelastic scattering is occurring. If you look at this spectrum, you conclude that the argon 2+ yield is maximized at 0.3 cycles of the mid-infrared. Or to say that in other words, the argon double plus yield, I'm sorry, this is the, let me see, what do I have here? This is not the, this is the error. You can convert that phase into a time, and that time is on the order of like 150 attoseconds. So we can time when this set of quantum trajectories are launched with about 100 attoseconds of precision.
You have 5 minutes remaining?
Yes, good. And the point here is we measure a phase of 0.3 cycles. And classically, from this 3-step model, where the return energy is maximum, this 3.17 UP quantity actually occurs at, you would calculate 0.297 of the mid-IR cycle. So it looks like we're indeed timing this recollision process, and it's in agreement at least with this simple classical picture. We're not interested in the future of like studying the classical picture anymore, but this was certainly our test bed to see if this new way is working. This shows again the same type of thing of how we can clock the double ion yield, the elastic scattering against these direct electrons, and that is shown here. So what we find is that the cutoff of the what we call the rescattered electrons occurs at 0.27 cycles. The argon, as I said, was 0.3. And again, this is nominally in agreement with what you would expect from the recollision model. Okay, I'll skip this since it's not showing. The point of that is we actually can extract new physics from these type of experiments that you would never see in just a typical strong field experiment. Okay, so let me conclude here. What's the future for this type of quantum trajectory selector? Well, first of all, we believe now we've kind of added a new tool into the toolbox of attosecond physics for studying recollision physics in any situation, in gases, in solids, okay. Our interest is we know that classical behavior breaks down, okay. For instance, we see that we can initiate double ionization by exciting the system below the in the classically forbidden region. So there's quantum aspects here that are occurring in these strong field processes, which we believe now we can get a closer look at it. Another interesting experiment that we like to do is right now what we're doing is exciting out of the valence state of the atom at the threshold. But there's no reason we have to excite the valence state. We can excite a core state, right? The XUV cone, but we can shape it and we can extend it out to 100 volts or so. So the idea is, instead of exciting the valence, excite the core to near threshold. And now drive that electron that that was formed by core excitation. Now the kind of interesting part is, if I excite the core, there's relaxation, right? It's an excited state of the system. So the core is going to relax either by Auger or fluorescence. Fluorescence is not interesting to us. But Auger takes place on the 1 to 5 femtosecond time scale. So now what we're doing is driving this electron optically in the few femtosecond range, and we have the core that wants to relax during this time. So as this electron propagates, the core actually changes, and we can probe that. Then we have played around with the idea of perhaps doing wave packet holography using this technique. And we think, in fact we know, we can now clock the dynamics in more complex systems like molecules. I'll just show you here as a teaser. Here is CO2 in this quantum trajectory selector. So in this two-color field, okay, what you see is you produce the double ion of CO2, and it oscillates at 2 omega, like we saw with argon. But likewise, you can see the phase dependence in the fragments. So now we can actually time when fragments.
Okay, we're out of time. So maybe real quick, any quick questions?
Are you finished, right?
Yeah, I was finished.
Sorry,
Yes.
just a stupid question. What was the pulse rate of your laser, the near-infrared laser at the start that starts this process?
Say that again.
Rep rate of light.
The rip rate. In our laboratory, we have kilohertz lasers, but you can do this at whatever rep rate.
But what's the pulse width? What's the
The pulse width, we're making trains, so our pulse widths are long, they're like 40 femtoseconds, okay? Yeah, but you could do this with an isolated pulse if you had, you know, a kind of 5 femtosecond drive.
Can you tap power out of this at all? Has it got any repercussions for real life?
So one thing that I think now you would want to try is to go back to the first experiments where they were trying to optimize the number of photons in the harmonic process. I think now, following this prescription, there's a chance of seeing enhanced harmonic generation.
Okay, thank you.
Well, thank you so much. I'd like to present this certificate for your speech.
Okay, thank you.